Okay, in this video that I'm going to do for you right now, I'm going to give you the theory behind weak acids. And in subsequent videos, I'll show you how you can work some of those problems. So, we were talking before about strong acids. Strong acids, clearly, are different than weak acids. Strong acids ionize completely in water. You can look at that as being a reaction. So HCl, for example, is a strong acid. When HCl is put into water, it reacts all the way, 100%, full ionization to form hydronium ion and chloride. If we start with half molar HCl, we end with half molar hydronium ion, and the pH, therefore, is the negative log of that half molar. Weak acids, on the other hand, a little bit more complicated. Weak acids do not ionize completely. That is the difference. Because weak acids do not ionize completely, they are not a reaction with water, they are an equilibrium. And so, already in your head, I hope you're thinking, okay, reactions require stoichiometry, equilibriums require ice tables. And honestly, there are a lot more weak acids than there are strong acids. So the strong acids, hydrochloric, hydroiodic, hydrobromic, nitric, there's fewer strong acids than there are weak acids. The most common weak acids that I'm going to use is HF, that's hydrofluoric. That uh, goes against the trend. The trend for all of the other halogenated acids, chloric, bromic, and iodic, those are all strong. Hydrofluoric is an outlier. It is a weak acid. The other really common weak acid I use is acetic. So I've been after you to memorize that acetate ion and what the chemical formula is for acetic acid since last semester, and here it is again. Acetic acid is a weak acid. Another one that is frequently used is HCN, that's hydrocyanic acid, but there's also tons and tons and tons and tons more. If it is not one of the strong that you need to memorize, it is a weak acid. Okay, so let's look at the equilibrium that happens between acetic acid and water. So acetic acid is a weak acid. Arrhenius tells us that one of the definitions of an acid is that when you put it in water, it forms hydronium ion. Please note, this is an equilibrium. This is not a reaction. So acetic acid reacts with water to form acetate ion and hydronium ion. So since this is an equilibrium, we can write the equilibrium constant expression. Remember, the equilibrium constant expression is products to their orders divided by reactants to their orders. So we're going to put this in terms of concentrations. So the equilibrium constant for this reaction is the concentration of acetate ion to the first power times the concentration of hydronium ion to the first power divided by the concentration of acetic acid to the first power times the concentration of water to the first power. Now, we're going to do something a little fancy here. Let's talk about the concentration of water. Water is the solvent. We have massive quantities of water all over the place. And basically, the concentration of water can be thought of to be about, 55.5 molar. That's gigantic. That's huge. We're never going to have anything that's 55 molar. So it is in gigantic excess compared to the acetic acid. And we can say that the concentration really doesn't change during the course of the reaction, right? We've done that assumption before where we've assumed that the change in the concentration is negligible. The change in the concentration of water here, super negligible. It's a pure liquid. Liquids and solids don't typically appear in equilibrium constant expressions. So basically what we're going to do is we're going to get water out of there. We're going to ignore water. And we're going to rename this equilibrium constant as a Ka. Ka is equal to acetate to the first times hydronium to the first divided by acetic acid. You can see they're identical to each other. The only difference is we've gotten rid of water. So what does that little a mean? Ka is called the acid dissociation constant. I can never, I'm sorry, the acid ionization constant. Ionic compounds dissociate, acids ionize, so this is the acid ionization constant. And we can look at it just like we've looked at other equilibrium constants. It's going to tell us the extent to which the acid ionizes. So if you have a Ka that is very large, that is a strong acid. I don't want to say that it's a strong acid. Just kidding. Okay, I want to say, because it's not one of the strong acids. Any weak acid is at equilibrium, so I don't want to say that it's a strong acid because that I think could get a little bit confusing. But if you have a Ka that's very large, that means that it's going to have a low pH because it is a product favored equilibrium. Right? So if we have, yeah, I think I'll just do it this way. If we have a Ka that's very large, that means we have more products present at equilibrium than we have reactants. That means our acid ionizes to a great extent. We have lots and lots and lots of hydronium ion present at equilibrium. Since the pH is the negative log of the hydronium ion, the more hydronium we have, the lower the pH. The lower the pH, the more acidic it is. However, if you have a Ka that is very small, again, I'm not talking negative, I'm talking, 0.0001, 1 times 10 to the minus 4, somewhere along there. But if you have a Ka that is very small, that is a reactant favored equilibrium. And it will still have an acidic pH, okay? We're still an acid. We're still going to have a pH less than 7, but it's going to be a larger pH, less acidic than an acid with a large ionization constant. So large ionization constant, very acidic, low pH. Small ionization constant, higher pH, due to it being reactant favored. So again, I want to remind you about what these equations are. The equations that are important is that pH is equal to negative log of the hydronium ion concentration, and then 10 to the minus pKa, 10 to the minus pH, I'm so sorry, 10 to the minus pH equals the hydronium ion concentration. Hold on a second, I'm really confused. I'm going to be talking about Kas in a second and pKas, but pH is the negative log of the hydronium ion. Negative 10 to, 10 to the minus pH is the hydronium ion concentration. Okay, let's talk about these Kas now. So, just the same as those equations I just gave you. pH is the negative log of hydronium ion. 10 to the minus pH is the hydronium ion concentration. We can do the same thing with Kas, okay? So we have this thing that we're going to define as the pKa. The pKa is the negative log of the acid ionization constant. So the negative log of the Ka is the pKa. And 10 to the minus pKa gives you the Ka. Really, this pKa process is a way of taking numbers that are really small or really large and making them something that we can handle. So, for example, if we had a hydronium ion concentration that's 1 times 10 to the minus 7th molar, the pH is 7. So it's easier to talk about a pH being 7 than it is to talk about a hydronium ion concentration being 1 times 10 to the minus 7th. That's the value of pH, because it takes unwieldy numbers and makes them easier to talk about. The exact same thing is going on here with the pKa. I can tell you that acetic acid has a pKa of, I want to make sure I'm not going to lie to you. I have it memorized, but not exactly memorized. So the pKa of acetic acid is the negative log of the Ka, which is 4.74. Okay, so that's an easy number for me to say. The pKa of acetic acid is 4.74. So what is the Ka for that? All right, 10 to the minus 4.74 is 1.82 times 10 to the minus fifth. That's a much harder number just for me to say out loud. And so that's the value. Okay, so now let's try to understand what this pKa really means. So acetic acid has a pKa of 4.74. Hydrofluoric acid has a pKa of 3.14, which is the stronger acid. That question can also be rephrased as which ionizes more completely. That can also be rephrased as which is more product favored. How else can this be said? And I'm telling you, this is a question that chemists ask all the time. Oh my gosh, all the time. What's the stronger acid and how do you know? And this pKa thing will come back over and over again through organic chemistry and biochemistry. You need to know about these pKas. So I need to get you introduced to them now so that you can carry them forward with you as you continue on. So a lot of times students get a little bit confused about it. One way that you can do it is absolutely to go from the pKa to the Ka. Okay, so we did that for acetic acid. pKa of 4.74 gives you the Ka of 1.82 times 10 to the minus fifth. pKa of HF, 3.14, gives you a Ka of 10 to the minus 3.14, 7.24 times 10 to the minus fourth. Now you can look at the two of these and be like, okay, which one is going to ionize more completely? That's going to be the one with the bigger Ka. So that means that HF is our stronger acid. But you can shortcut around that just by looking at the pKa. The way I think about pKa is it's like how much does the acid want to hold on to its proton? So if you look at HF, HF wants to hold on to its proton 3.14. Acetic acid only wants to hold on to its proton 4.74. Okay, so HF does not want to hold on to its proton as much as acetic acid wants to. HF wants to get rid of its proton more than acetic acid wants to. It only wants its proton 3. Acetic acid wants its proton 4. HF is going to get rid of its proton more easily than acetic acid will. And so that's how you can think of acetic acid being a weaker acid because it wants to hold on to its proton more than HF. So let me write that down so you guys have a little bit of words here, okay? So pKa is how much the acid holds on to its proton. The smaller the pKa, the less strongly the proton is held onto. And if it's held onto not very strongly, it's donated away. Water can steal it more easily. So the smaller the pKa, the less strongly the proton is held onto, and therefore the stronger the acid. Okay, so to finish this video out, I'm already at 15 minutes, but in order to finish this video out, let's do one example of how we can use equilibriums and this idea of Ka to solve some equilibrium problems. So the question is, what is the pH of half molar acetic acid if the Ka is 1.8 times 10 to the minus fifth? Now, what is the pH is a very innocuous looking question, but you have to do a lot of work in order to get what is the pH, especially when you have a weak acid. So the way you analyze this, what is the pH is also basically asking what's the hydronium ion concentration, because again, pH is negative log of hydronium ion. That's how we're going to get what the pH is of the solution. So now the next part of this is, okay, acetic acid, is that a strong acid or a weak acid? Acetic acid is one of the weak acids. One of the ways you know that is it's not one of the strong that, I'm asking you to sort of memorize. And I've given you a Ka. The Ka is times 10 to the minus fifth. That tells you that it does not ionize completely. So there are multiple ways that you can get at that this acetic acid is a weak acid. Since acetic acid is a weak acid, it is an equilibrium. So acetic acid is put into water and it forms an equilibrium with acetate ion and hydronium ion. Now we're lucky this is 1-to-1, but remember for other equilibriums, watch the coefficients. Those coefficients matter in a number of places. So watch the coefficients. Here it's all 1-to-1. Now we're going to do our ice table. The initial concentration of acetic acid, is 0.5. We don't care about water. You're going to see me do this a lot over the next couple of weeks, but we don't care about water. It doesn't appear in the Ka expression. It doesn't change its concentration. I'm never going to ask for the concentration of water because the concentration of water is going to stay like 55 molar. So we don't care about water in the equilibrium table. We have no acetate and we have no hydronium to start with. The equilibrium is going to shift to the right. We have no products. We have to make some products. So this is going to shift by minus x because the coefficient in front of the acetic acid is 1. Please don't skip this. The coefficients matter. So we're going to subtract x from acetic acid. Water doesn't matter. We're going to add 1x to acetate. The coefficient is 1. Don't lose it. And we're going to produce hydronium also by 1 because the coefficient is 1. At equilibrium, the concentration of acetic acid is 0.5 minus x. We don't care about water. The concentration of acetate ion is x. The concentration of hydronium ion is x. Now, we're trying to solve for the concentration of hydronium ion because we want the pH, and the pH is the negative log of that. So we're trying to solve for x. We're given the equilibrium constant. That is how you know that we're trying to solve for x. There's no way for us to know x directly. And so we're going to make that assumption. We're going to assume that the change in the concentration of the acetic acid is negligible. We're going to assume that at equilibrium, it's going to be about half molar. So Ka is equal to products to their orders divided by reactants to their orders. So that's acetate ion to the first, hydronium ion to the first, divided by acetic acid, also to the first. So now we can plug things in. 1.8 times 10 to the minus fifth equals x times x divided by 0.5 because we made that assumption. So let's solve for x. 1.8 times 10 to the minus fifth times 0.5, and then the square root of that answer gives me that x is equal to 0.003. We made an assumption. Check the assumption before you go further. Check the assumption. Checking the assumption means we're going to put 0.003 divided by 0.5 times 100. If it's less than 5%, then the assumption is valid, and we can continue on. If it's more than 5%, we would need to use the quadratic equation. It's 0.6%, so check, check. Our assumption is valid. Okay, so now we know what x is equal to, 0.003. All we're looking for is what is the pH of the solution. Well, the pH of the solution is the negative log of the hydronium ion. At equilibrium, the concentration of hydronium ion is 0.003. So now the pH of this solution is the negative log of 0.003. The negative log of 0.003 is 2.5. Now, I really want to point something out here. This is acidic. 2.5 is still pretty acidic, right? pH of 0 to 6.99 is an acid. 2.5 is pretty acidic. So even though I'm saying that acetic acid is a weak acid, even though I'm saying that it only ionizes, with an equilibrium constant of 1.8 times 10 to the minus fifth, that doesn't change the fact that it is an acid. If you flip back to your notes that we did earlier this week, we did half molar HCl. HCl is a strong acid, it ionizes completely, and half molar HCl had a pH of 0.3. Here we're doing the pH of acetic acid, which is a weak acid, pH of 2.5. So it is still acidic. It is just not as acidic as hydrochloric acid. All right, I'm going to finish this up here, and I'm going to do a couple of more shorter videos on solving other equilibrium problems involving weak acids.